Hello students, this is the fourth video of this chapter CPU and the topic is types of CPU organization. First of all, we need to know what is the use of knowing the type of CPU organization. Actually, the type of CPU organization determines how an instruction should be written for that CPU. For example, you are familiar with this instruction, add x. X means B, C, D, whatever it is. Okay. I can write add R1, R2 also. You are not familiar with this type of instruction. Still, I can write add R1, R2, R3 also. Right. So this is determined by the type of CPU organization. Okay, I'm giving an example. Try to relate it. Suppose I say come to a person. Okay. I can also say come in. Okay. Or else come in to this room. Right? In all these three cases, the meaning is same, but the way I am telling is different. But the meaning is same, right? In these cases also, the meaning is same, that I am instructing the computer to add. Okay? But the way of telling is different. Okay? So this is determined by the types of CPU organization. So clear? Why should we study this topic? Okay, let's move on. There are three types of CPU organization. But before telling the name, I would like to say some introduction about it. You remember the instruction format? There is an mode field, opcode field, and address field. You remember this? Mode field, opcode field, and address field. Now, this address field determines the types of CPU organization. Actually, how many number of address fields will be there determines the types of CPU organization. Are you familiar with this also? This opcode, address of source operand 1, address of source operand 2, address of destination operand, address of next instruction. Are you familiar with this? I think I told it in your class. Whatever. It is also an instruction format, right? Now, the number of address fields determines the type of CPU organization. Now, finally, let's come to the type of CPU organization. Three types are there. Single accumulator organization, general register organization, and stack organization. In single accumulator organization, you just remember two keywords. One is implied accumulator. ACC, I'm writing ACC. And second one is one address field. Implied accumulator means that in the instruction, we won't write the name of accumulator, but it is implied. You know the example of this. Add. I'm writing X here, but you are familiar with this. Add B, because it means the content of accumulator is added with the content of B register, right? and the result is stored in accumulator. You are familiar with this, but now just keep in mind. Okay, so implied accumulator means we are not mentioning the name of accumulator in the instruction in this example, right? Okay, and one address field means that in the instruction only one address can be mentioned. Okay, may it be register, may it be memory address, whatever, but only a single address can be there, like this. So add x means the content of accumulator is added with the memory word of this location x, and the result is stored in the accumulator, but the role of accumulator is not mentioned in this instruction. So this is all about single accumulator organization. Got it? In general register organization, there are two types. One is 2 address field, another is 3 address field. Okay, let's first consider 3 address field. Okay, that means in the instruction we can mention only 3 address fields, right? Example, add R1, R2, R3. That means these are the source and this is the destination. In RTL, that means in register transfer language, you already studied that. For example, it is move R1, R2. That means the content of R2 is moved to R1. That means it is source, it is destination. So source is in the right hand side and destination is in the left hand side. For example, I mentioned this, remember. Okay, so the example for 3 address fields is add R1, R2, R3. So in RTL I can write it as R2, content of R2 plus content of R3 are added and the result is stored in R1. So these are the sources and it is the destination. Clear? In case of 2 address fields, we can mention only 2 addresses. For example, add R1, R2. Here are 2 operands or 2 locations, whatever. So where is the address stored? See, content of R1 and content of R2 are added and the result is stored in R1. Why in R1? It is in the left hand side, that's why. If I would have written add R2, R1, then the content of R2 and content of R1 are added and the result is stored in R2 because it is written in the left hand side. Clear up to this? Okay. In stack organization, this is the third category. In stack organization, we have push instruction, pop instruction, and some zero address instructions. Means push X means that we have to push an item from this location of memory to the top of the stack. And pop X means we have to pop or delete the top of the stack element and